We now discuss the definition of product measures. So in the development of these product measures, we will start with two measure spaces and then proceed with induction or recursion for a finite number of measure spaces. So to start, let us consider two measure spaces, x sigma mu and y tau mu. And recall that the Cartesian product of two sigma algebras is the collection of Cartesian products. The first set E is in sigma, and the second set F is in tau or T. And recall that the product sigma algebra is the sigma algebra of the Cartesian product. And this follows from our previous discussion. Okay, now according to the following identity, so E, let's say cross F, intersection of G cross H, where we can write this intersection of Cartesian products as the Cartesian product of intersections. We can see that sigma cross T is closed under finite intersections. So this implies that the Dynkin system generated by the Cartesian product sigma cross T is the same as the sigma algebra generated by the Cartesian product. So put in another way, the product sigma algebra is also the Dynkin system generated by the Cartesian product of the two sigma algebras. So we now define the so-called sections of a subset of the Cartesian product of x and y. So given, let's say, an ordered pair in the Cartesian product, the section on x of the set A at the point y. So this is the set of all points, let's say u in x, such that u, the ordered pair uy, is in A. And obviously, by definition, this is a subset of x. And analogously, the section on y of the set A at the point x is the set of all points v in y, such that xv is in A, and this is a subset of y. So to have a geometric interpretation of this, you consider x as your horizontal axis and y as your vertical axis. The Cartesian product would be this rectangle. And let us take a subset A, a subset of the Cartesian product. And it is highlighted here by a blue. And pick a point, an ordered pair, xy, on the Cartesian product. So in this illustration, we took a point inside A. But of course, you can also take a point outside A. So you draw this cross here. Okay, so the section on X would be the projection of this line segment onto the x-axis or x set, and that would be this region here, and this will be the section on X of A at the point Y. Analogously, the vertical component, this one, is the section of A on Y at the point X. So these sections, therefore, introduces set valued maps. So the section on X of A, so it takes an argument in Y. So it's a mapping from Y to the power set of X. And similarly, the section of A on Y is a mapping from X to the power set of Y. Well, if we, instead of a general set A, which is a subset of the cross product, what if we also have a Cartesian product of subsets of X and Y? How do these sections look like? So take a subset E of X and a subset F of Y. Then you can immediately show that the section on X of E cross F at a point Y is either, so this would be the full set E if Y is in F. Otherwise, that is, if Y is not in F, then the section would be empty. So if you, let's say, have a point wherein the Y component is outside the rectangle, so the section would be empty. And in a similar manner, the section on Y of the Cartesian product of X is either the set F or the empty set, depending on whether X is in E or not in E, respectively. So here, of course, the pair XY is in X cross Y. Okay, so these are some properties of the section for, or this is a characterization of the sections on X and Y if you have a Cartesian product of two sets. So here we said that the values of the sections of a subset is either in the power set of X or in the power set of Y. More can be said if A is an element of the product sigma algebra. And let us state this as a lemma. So consider an element A in the product of sigma algebra and an ordered pair in X cross Y. Then the sections, so for Sy, this is a map from X to the power set of Y, but we can say that it maps to measurable sets in Y. Namely, you have the sigma algebra tau or T. And analogously, the section on X is a map from Y to sigma. So let us look at the proof. And here we want to show the following. The section of X at Y is in sigma for all y and capital Y. So here we aim to show the second conclusion. The proof of the first one is similar, so we do this only for the second map. Let us denote by script S the set of all elements in the product sigma algebra wherein this conclusion is valid. Okay. Note that according to the previous remark here, from the previous remark, we know that as sigma cross T. So if E is in sigma or F is in tau, if E is in sigma, then we know that the section is an element of sigma cross T. Then therefore, this implies that sigma cross T is a subset of S. So you can take A to be the Cartesian product of E cross F, where E is in sigma and F is in tau. And you can see that according to these equations here, you either have NT, you either have E or F, then we have this. Okay. So we claim that S is a sigma algebra. If this is the case, if this claim is valid, then okay, we know that the product sigma algebra is the sigma algebra of the generated by the Cartesian product. And this is a sigma algebra that contains this one. So therefore, this is a subset of S. However, by definition, all elements of S belongs to a sigma cross T. So this implies that S is sigma cross T. That is, the section is in sigma for any Y in capital Y and A in sigma cross T. And this is a restatement of this, or this one. Okay. So we need to put it here for emphasis that A is in sigma cross T. Thus, it suffices to show that S is a sigma algebra. And here, the whole space that is X cross Y, this is obviously in sigma cross T, because both of these are sigma algebras. This implies that X cross Y is in S according to this one. Next, we establish a closure under complementation. So if A is in S, then you can look at the section of the complement at the point Y. So Y is in capital Y. By definition, well, you can prove this easily by double set inclusion. This is the complement of the section of A at Y. Take note that if A is in S, the defining property, okay, of S means that this section is in sigma, hence the complement is also in sigma. Thus, this one is in sigma, therefore A complement satisfies the property to be an element in S, so it's in S. Next, we consider closure under countable unions. So take a countable sequence of elements in S. Then for each Y in capital Y, we have, okay, the definition of S means that the section of A sub n on X at the point Y is in sigma for all n. Hence, again, by a double set inclusion, you can easily see that the section of the union at Y is nothing but the union of the sections. Hence, since sigma is a sigma algebra, this is also in sigma. Thus, the union is also in S. So therefore, these 3 points here imply that S is a sigma algebra, and according to what we have discussed earlier, this will imply that the section of an element in the product sigma algebra on X maps Y into a sigma. The first statement can be handled in an analogous manner. Okay, so in the following theorem, we consider a function of 2 variables. So let us consider a map f from x cross y into r. Suppose that this is measurable with respect to the product sigma algebra and the Borel sigma algebra. So as an illustration, think of the 3-dimensional plane where here you have your x-axis and here you have the y-axis. For each ordered pair in x cross y, the following trace maps. So for a fixed y, we have a function of x. So this is a mapping from x to r. And on the other hand, for a fixed x, we have a map from y to r. These trace maps are sigma br and t br measurable. respectively. So in this figure, for a, let's say if we fix x, so we will get this trace or slice of the function f. So this is a function of y. So this curve here is parallel to the let's say YR plane. On the other hand, for a fix y, you have this trace colored in green. So now you have a function of x, and this would be parallel to the x r plane. So these are what we call the trace maps. Given a fixed argument, you can consider the function as a function of the other argument. For the proof, for each, let's say B, Borel set in R, and an ordered pair xy in x cross y, you can easily show that the inverse image of this trace function for fixed y of B is nothing but the section on x of the inverse image B at the point y. And similarly, for a fixed x, you get the corresponding section on y at the point x. Okay, so take note that by measurability, this inverse image is in the product sigma algebra. Okay. Now, according to the previous lemma, the section maps y into sigma and x to t. So this implies that, okay, this section must be in t. This must be in sigma. And this, since this is valid for any Borel set, this implies the measurability of your trace functions. Let us now consider an additional assumption that the sigma algebras or the measure spaces are sigma finite. And we look at the compositions of the sections with respect to the given measures. So for this, we have the following theorem. So consider two sigma finite measure spaces. If I take an A in the product sigma algebra, then if I take the section, okay, we know that this maps y into sigma. Hence, we can take the composition with the measure mu. Then this is a non-negative measurable function with respect to y. And analogously, you have for the section on y, but now this is a measurable function with respect to x. And well, non-negativity follows immediately from the fact that measures are non-negative. Moreover, we can calculate, okay, the Lebesgue integrals. So here we have the section, the composition of measure nu and the section on y. This is a function of x, so we integrate with respect to the measure nu. This is the same as the Lebesgue integral of the first composition, that is mu and the section on x. And here we need to use the measure nu. Again, we use the same trick as before. We first consider as a first step the case where mu and nu are finite. And then the sigma finite case will follow from this one and the definition of sigma finiteness. Let us define, okay, let D be the set of all A in the product sigma algebra such that, okay, let us name this as 1, 2, and 3, such that 1, 2, and 3 hold. Okay, so let us establish the following property. We will show that the Cartesian products of the sigma algebra lies in D. And for this, let us take an element of the Cartesian product of the two sigma algebras. Okay, since recall from the above remark, and what we are referring here is this one. So let us look at the second case. So the section, if x is in E, is equal to f. So if we take the measure, we either get the measure of f or 0, depending whether x is in E or not. And this means that the composition of this, okay, we have here E cross F is equal to the measure of f with respect to nu times the characteristic function of B. Okay, since when you evaluate in x, this is either 0 or 1, depending whether x is in E or not. And this is clearly, we note that this is a step function, okay, in x, non-negative step function, and we know that non-negative simple functions, I should say, non-negative simple functions are measurable. Okay, similarly, And let us first compute the integral. Being a simple function, we know that the integral is so you take the coefficient, that's the measure of f, times the measure of b. And in a similar manner, you can show that mu, composition with dissection on x of the Cartesian product of E and F, is the same as mu of E times the characteristic function of f, and this is a simple function in y, hence a measurable function. And you can calculate the Lebesgue integral equals f. This must now be in y. And this is the same as mu of E, mu of f. So if we label this, take note that this is the second. Yes, it's the second. This is the first. And if you combine 3a and 3b, you get a 3. Since, of course, these two are equal by commutativity of product in real numbers. So to conclude, we see that the Cartesian product is in D, since the three properties are satisfied. Okay, so that's the first one. Next, we show that this D is in fact a Dinkian system. And this will establish our first step, since in this case, if indeed D is a Dinkian system, D is a subset of the product sigma algebra by definition. We know that this is the same as the Dinkian system generated by the Cartesian product. And since D is a Dinkian system containing the Cartesian product, we have this inclusion. Therefore, D is equal to sigma cross T. So going back to the definition of D here. So this means that the three properties 1, 2, and 3 are indeed satisfied by any element on the product sigma algebra. And this is what the theorem is mentioning here. Of course, this will only be the proof in the case where mu and mu are finite. So again, here it is enough to consider or to establish that T is a Dinkian system. Okay. First, since x cross y is in sigma cross t, and sigma cross t is a subset of D, according to the previous discussion, we have follows immediately that this is in D. Okay, so that's the easy part. Next, we establish the closure under complementation. Okay, then let us look at the section of the complement and composition with mu. So according to the previous discussion, this is this one. Okay, and this is the same as well, according to the finiteness of nu, this is nu of y minus nu of sy. And as by a similar calculation, we have the following. Now, this is an element of n plus. This should be in y. This is also an element of m plus x. According to the fact that a is in D, script D. Okay, then from this you can now easily see that the difference of two measurable functions is also measurable. So this is e n plus yt, and analogously for the second one. Also, let us compute the integrals. So integrating the first one, I think we have a mistake here. Yes, this should be the other way around. So let us correct this statements here. This should be in m plus x sigma. This must be in m plus y t. Okay, so this integral here makes sense. Okay, so with this, let us apply the first according to the above equation. This is nu of y minus nu of the section on y d mu. The first bilinearity of the Lebesgue integral. So The first one would be nu of y, nu of x minus the Lebesgue integral. Okay, here we apply the third property for applied to A. Okay, and here I'll just interchange the two numbers, but the second term can be written as, okay, according to the third property applied to A, it's equal to this one. So reversing the above process, this can be written as follows. So as a single integral, again by linearity, and applying this second equation here is the same as the integral of mu of the section of the complement. So this verifies the three properties in D. Thus, the complement of an element in D is also in D. Okay, so now let us prove the case of closure under pairwise disjoint union. So take a countable sequence of pairwise disjoint sets in D. Now, if you apply sigma additivity, nu of the section on Y of the pairwise disjoint union we said a while ago that this is nu of the union of the sections so sigma additivity of nu implies that this is the sum and as you know, the series can be written as the limit of the partial sums. Okay, since an is in D, this must be measurable, a non-negative measurable function defined on sigma, on x, okay? Hence, therefore, the sum and therefore the limit. So this must be in m plus x sigma. Okay, so let us emphasize this one here. And in a similar manner, you can proceed interchanging x and y and then mu by nu. You get the following. And this is also a non-negative measurable function on y. Okay, so this proves measurability. Now, and non-negativity. Now we need to establish the equality of the integrals. Okay, so let's start with the section on y. So that's the integral over x of this section on Y. So let's copy the left hand side. So that's mu of Sy of the union. And we know that this is according the highlighted parts here. And we can interchange, okay, the sum and integration in virtue of the monotone convergence theorem. Now, if you apply the third property for an, the integral over x can be replaced by the integral over y, but now you take this composition with respect to the section on x. And once again, you go backwards, you apply monotone convergence theorem, and then applying this identity, and according to these calculations, we can now conclude that therefore the union of an is in D, since this establishes the required third property. So therefore, D is closed under pairwise disjoint union. It is closed under complementation. The whole product set x cross y is also in D. Hence, this is a Dynkin system. And this implies that the three conditions in the statement of the theorem is valid for the finite case. So let us now move to the sigma finite case. Then this implies that there exists a sequence xn in sigma, another sequence yn in tau, such that mu of xn is finite, mu of yn is finite, xn increases to x, and yn increases to y. Okay, if the original set is not increasing, of course you can construct an increasing sequence wherein it will increases to x. Okay, so now given, let's say, well, let's take an A in sigma cross T. Then, okay, you can show that this composition, but now intersecting in the restricted Cartesian product, that's xn cross x. This is evaluated at x. Okay, so for x in capital X, this is the same as the following. So you just take the composition of this one. So Sy, evaluate this as at x, intersection yn multiplied by the characteristic function of xn. Okay, so let us ignore the argument for simplicity. But it should be noted that this must be taken pointwise. According to step 1, this is measurable by step 1 by step 1. Okay. Hence, since xn is also measurable, this is in m plus x. And similarly, doing this for the other part. Let us remove here the argument now. This is the same as mu of the section intersection xn times the characteristic function of yn. And this is in m plus yt by step 1. Okay, furthermore, if we, let's say, apply step 1 to the finite measure spaces. So here we consider the restriction sigma algebra, the same measure, okay, but the sets are now different. So if you do this, okay, so let us look at this function here. So copying that one, this should be yn. Here you have the indicator function on xn, d mu. So this is, okay, the same as the integral over xn by definition of the integral over a subset and we know that this is the same as the integral over yn of mu. Intersection xn d nu. Here we applied the property, the third property. Here, the intersection, since we are dealing with the restriction sigma algebras. And you can go back, of course. It's now yn of mu of sx a intersection xn times the indicator function of yn d nu. But now this should be y. Okay, so this establishes so far having these terms. And this is true for any n. Since, okay, you can see that sy, the section of sy, okay, so looking back at this, so you observe that this section sy intersection with intersection of xn cross yn. This one increases to, in the sense of functions, of course, sy of a, and similarly for sx, the section on x. Continuity of mu and nu imply that the limit as n goes to infinity of mu of let's say u of sy is the same as mu of sy. Okay, so we said that each of these are measurable, non-negative measurable. Therefore, this is also non-negative measurable. And this would be in with respect to y. And we do this also for the other function, the section on x. So this should be usx. In order for the composition to be well defined. Okay. This is the same as nu of sy of a. Continuity from below of a measure. X sigma. Okay, so this establishes the measurability of these compositions. Moreover, the integral, let's say over x of this composition, okay, d mu. You apply here the monotone convergence theorem, so that this will be the limit as n goes to infinity of the integral of x over x of this section. Okay, so take note that this one here, is the same as this. And we have shown that the integral of this is the same as the integral of that. As a result, the integral of these two are the same. So here we have the limit as n goes to infinity of mu of the section on x du. Okay, so let us emphasize that one. Let's say this is the equation. Let's say this is A, this is B, and this is C. Here you apply A, B, and C. Applying the monotone convergence theorem, once again, we now obtain this equation. And this is the third property. This is the second, and then I think this is the first. Therefore, the three properties stated by the theorem is also valid in the sigma finite case. And this establishes the theorem.